Greetings to all viewers. This is Professor Ankit Singh. In my previous lecture, we had discussed the different types of sight distances. Now we will move ahead and start horizontal alignment. Various design factors to be considered in the horizontal alignment are design speed, radius of circular curves, type and length of transition curves, super elevation, and widening of pavement on curves. Now these are the different factors or design factors that we consider within horizontal alignment. We will discuss each of these factors, derive their formulas, and study their importance in our later on classes. The alignment should enable consistent, safe, and smooth movement of vehicles operating at design speeds. It is necessary to avoid sharp curves and reverse curves which could not be conveniently negotiated by the vehicles at design speed. Okay, these are few conditions that we need to satisfy while we set our horizontal alignment. We have already discussed these points in my previous classes when we were discussing alignment or setting of alignment. Improper design of horizontal alignment of roads would necessitate speed changes resulting in increased vehicle operation cost and higher accident rate. Okay, if there is an improper design of the horizontal alignment, then this may lead to increased cost and also increased accident rate. Okay, it may hamper the safety of the road users. Okay, the first design element is design speed. We already know what a design speed is. Design speed is that speed for which is the maximum speed for which the road is being designed. So any vehicle is allowed to travel at a maximum speed of design speed for that particular road. The design speed, as noted earlier, is the single most important factor in the design of horizontal alignment. Okay, it is important for design of any geometric element. Okay, the design speed also depends on the type of the road. For example, the design speed expected from a national highway will be much higher than a village road, and hence the curve geometry will vary significantly. Okay, the design speeds vary for different type of roads. Okay, the design speed for national highway and state highway would be more as compared to major district road, other district road, and village roads. The design speed also depends on the type of terrain. A plain terrain can afford to have any geometry, but for the same standard in a hilly terrain requires substantial cutting and filling, implying exorbitant costs as well as safety concern due to unstable slopes. Okay, as the slope value increases, we need to decrease the design speed. Okay, therefore the design speed is normally reduced for terrains with steeper slopes. Okay, as we have already discussed earlier that there are four types of terrains that we consider. Okay, and we classify them based on cross slope percentage. Okay, IRC or Indian Road Congress has classified the terrains into four categories, namely plain, rolling, mountainous, and steep, based on the cross slope as given in the following table. Okay, there's a table given here for different terrains. The cross slope percentages have been specified by IRC. If the cross slope varies from 0 to 10%, then it is plain terrain, 10 to 25% rolling, 25 to 60 mountainous, and greater than 60% is steep terrain. Now, based on these terrains and based on the type of road, what IRC does is IRC provides a standard design speed values. Okay, so for NH and SH, for plain terrain the speed would be ruling design speed 100 kmph and minimum design speed of 80 kmph. Okay. Similarly for MDR, for different terrains, for ODR different terrains, and village roads. Okay, so these standards have been specified by IRC. The next geometric element that we design is horizontal curves. Okay, a horizontal highway curve is a curve in plan to provide change in direction to the center line of the road. Okay, so horizontal curve is used to join two roads which are moving in different directions. Okay, when a vehicle traverses a horizontal curve, the centrifugal force acts horizontally outwards through the center of the gravity of a vehicle. Okay, so this phenomena of centrifugal force we have already studied in our lower classes during our 12th, okay, in physics, that whenever a body or a vehicle traverses a horizontal curve, then it is subjected to a outward force which is known as centrifugal force. Okay, now this outward force, it is required that we counteract this outward force so as to provide safety and stability to our vehicle. Okay, the centrifugal force developed depends on the radius of the horizontal curve. Okay, if the radius of the horizontal curve is more, then the centrifugal force would be less. Okay, you need to imagine this. You see, when the radius is more, the higher the radius, the curve would be less sharper. Okay, so it would produce lesser centrifugal force, and as the radius reduces, the horizontal curve becomes sharper, and hence the centrifugal force induced would be more, and the speed of the vehicle negotiating the curve. Okay, so the centrifugal force would be higher for a vehicle traveling at a higher speed. Okay, this centrifugal force is counteracted by the transverse frictional resistance developed between the tires and the pavement, which enables the vehicle to change the direction along the curve and to maintain stability of the vehicle. Okay, now what we do is we try to counteract this centrifugal force using the frictional resistance from the road pavement. Okay, we have already studied about frictional resistance. Okay, there were two types of frictional resistance that the road can provide. One was longitudinal friction, the other one was transverse friction. Okay, here the case is for transverse friction. Okay, centrifugal force P is given by the equation. Okay, this is a standard equation. We know that P, or centrifugal force, is equal to W into V square divided by GR, where P is nothing but centrifugal force in the unit. W is weight of the vehicle in kgs. R is radius of the circular curve in meters. V is speed of vehicle in meter per second, and G is acceleration due to gravity, 9.8 meter per second square. Okay, the ratio of the centrifugal force to the weight of the vehicle, or P by W, is known as centrifugal ratio or impact factor. Okay, so in this formula, when you bring W to the left hand side, then this would become P by W, and P by W would be equal to V square by GR. Now we denote this P by W as the centrifugal ratio, or it is also known as the impact factor. Okay, the centrifugal force acting on a vehicle negotiating a horizontal curve has two effects. Okay, due to the centrifugal force acting on a vehicle, there can be two conditions: tendency to overturn the vehicle outwards about the outer wheels. Okay, there is the first tendency is to overturn the vehicle outwards, and the second condition is tendency to skid the vehicle laterally outwards. Okay, so if there is less amount of friction present on the road surface, then there is chance that this vehicle can either overturn towards the outer side, or it might skid laterally towards the outer side, okay, while traversing a horizontal curve. Now what we'll do is we will derive a formula to find out in what case the vehicle will overturn or it will skid transversely. Now let us consider the first condition, tendency to overturn the vehicle outwards about the outer wheels. Okay, so when we look at this diagram, the weight of the vehicle acts downwards from the CG. Okay, the width between the two wheels is B, and hence it can be denoted from the center as P by 2. Okay, P is the centrifugal force acting on the vehicle, okay, towards the outer side, and let H be the height between the road surface and the CG of the vehicle. Now the centrifugal force that tends the vehicle to overturn about the outer wheels B. Okay, this is the outer wheel and this is the inner wheel. This is the outer side of the horizontal curve and this is the inner side. The centrifugal force is acting towards the outer side, then there is a chance that this vehicle might overturn on this outer wheel B. Okay, on horizontal curve without super elevation is illustrated in this figure. Okay, here the road is flat, no banking has been provided, there is no super elevation provided. Okay, we'll study about super elevation in my next lectures. For now we are not considering any super elevation on the road. Okay, we are trying to counteract the centrifugal force using only friction. The overturning moment due to centrifugal force P would be, the force is P and the horizontal distance would be H, hence the moment would be P into H. This resisted by the restoring moment due to weight of the vehicle W and is equal to W into V by 2. Now P into H is a clockwise movement, okay, and this is resisted by the weight of the vehicle. Okay, weight of the vehicle, the force is W and the horizontal distance along the outer wheel is P by 2, and this is in the anti-clockwise direction. Okay, so the moment P into H in the clockwise direction is resisted by anti-clockwise moment of W into B by 2. Okay, where H is the height of the center of gravity of vehicle above the road surface and B is the width of the wheelbase or the wheel track of the vehicle. Hence the equilibrium condition for overturning will occur when? The equilibrium will be when the both moments are equated. Okay, so PH equal to W into B by 2. This means that there is a danger of overturning when the centrifugal ratio, okay, the centrifugal ratio is nothing but P by W. Okay, when you take W to the left hand side, okay, and H to the right hand side, you would get P by W is equal to P by 2H. Okay, so what is written here? This means that there is a danger of overturning when the centrifugal ratio P by W or V square by GR. We already know that P by W is equal to V square by GR. So either P by W or V square GR attains a value of P by 2H. Okay, when the centrifugal ratio attains a value of P by 2H, then there is a chance of overturning. Okay, and if this value exceeds P by 2H, then there is a definite chance of overturning of the vehicle. Okay. Now the second condition was transverse skid. Okay, transverse skidding effect. The centrifugal force developed has also the tendency to push the vehicle outwards in the transverse direction. Okay, consider this diagram. This is the outer side, this is the inner side. There is a frictional force Fa acting on wheel A and Fb acting on wheel B, wheel B being the outer wheel. Okay, hence there is more friction acting here than here. Okay, this frictional force can be split up as coefficient of friction into reaction at A, Ra, and at Fb coefficient of friction F into reaction at Rb, at B, that is Rb. Okay, so Fa is equal to F into Ra, Fb equal to F into Rb, and the other conditions are same. P, that is centrifugal force, is acting along the CG, and so is the weight of the vehicle. Okay, if the centrifugal force P developed exceeds the maximum possible transverse skid resistance due to friction, the vehicle will start skidding in the transverse direction. Okay, this is obvious. If this P value is greater than the friction that is offered by the pavement surface and the tires, then there would be a lateral skidding in the outer side. Okay, the equilibrium condition for the transverse skid resistance developed is given by, okay, we just equate the forces on the left hand side, the forces acting towards the left hand side and forces acting towards the right hand side. Then P would be equal to Fb plus Fa, because P is acting towards the outer side and Fb and Fa are acting towards the inner side. P is equal to Fa plus Fb. We split Fa as small f into Ra and Fb as small f into Rb, taking small f common, that is coefficient of friction. Then Ra plus Rb can be written as W. Okay, Ra plus Rb are the forces acting in the upward direction, is nothing but the force W, that is the weight of the vehicle, that is acting in the downward direction. Okay, hence P is equal to F into W. In the above equation, F is the coefficient of friction between the tire and the pavement surface in the transverse direction. Ra and Rb are normal reactions at the wheels A and B, such that Ra plus Rb is equal to the weight W of the vehicle, as no super elevation has been provided on this case. Now, since P is equal to Fw as obtained here, the centrifugal ratio, that is nothing but P by W, taking W on the other side, we'll get P by W is equal to F. Okay, so centrifugal ratio is equal to F. This is the equilibrium condition. Now, whenever the value of P by W exceeds the value of F, then there is a chance of transverse skidding. In other words, when the centrifugal ratio attains a value equal to coefficient of lateral friction, there is a danger of lateral skidding. Okay. Thus, to avoid overturning and lateral skidding on a horizontal curve, okay, so there are two conditions that might occur on a horizontal curve, that is overturning and lateral skidding. Now, to avoid this, the centrifugal ratio should always be less than B by 2H and F. Okay, the centrifugal ratio may be enough to cause overturning or lateral skidding of the vehicle if either the speed of the vehicle is high or radius of the curve is less. Okay, this I had discussed earlier, that the centrifugal force would increase if the speed is high, and it would also increase if the radius is less. If the pavement is horizontal across the alignment, the pressure on the wheels will be higher due to centrifugal force acting outwards, and hence reaction at Rb at the outer wheel will be higher. Okay, this we have already seen in this case, that the reaction RB would be higher than reaction RA. Okay, so these were the two conditions that occur due to movement of a vehicle on the horizontal curve. Okay, now next we would move on to super elevation. I'll discuss this in the next lecture. Thank you.